Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, everybody. Welcome back to another episode of the A-Level Cookbook. Today, we're going to be doing the AQA A-Level Chemistry paper 3 from June 2019. So sodium thiosulfate reacts with dilute hydrochloric acid as shown. Give the simplest ionic equation for this reaction. So what I'm going to do is I'm going to look at the ions that are present on either side and leave those ones out. So here, Na plus is the same as here, that Na plus. That Cl minus is still the same as the Cl minus. However, this whole S2O32 minus changes to an SO2 and an S solid. So those are probably going to be in the ionic equation, along with whatever it's causing to do that, which is probably going to be the HCl, because that's going to go from H plus to the entirety of the H2O there. So you could write all the ions out and then just cross them out, or you could do it that way. So the ion here that's doing this reaction is S2O32 minus. This bit here is going to be reacting with it, plus the 2H plus, gives you SO2 plus S plus H2O. There you go. The gas SO2 is a pollutant. State the property of SO2 that causes pollution when it enters rivers. Give an equation to show the reaction of SO2 with water. So here, the reason it's a problem is because it can be acidic. And you can't really just go ahead and say, oh, it's, although yes, it's soluble, the reason it's a problem causing pollution is because that it can dissolve to make an acid. So it says give the equation to show the reaction with water. So just write what you know, SO2 plus H2O, and then think what acid it's going to make. So the acid that it makes is H2SO3 when it does that. Now it says draw a diagram to show the shape of an H2O molecule and give any electrons or lone pairs and state the HOH angle. So oxygen, 1, 2, 3, 4, 5, 6. It likes to be in group 6. When it forms a covalent bond, it's sharing one of its electrons with another atom. In this case, it's H. So it's got this. So then that's a single line there, and then another single line here. So it has 2 bonding pairs and 2 lone pairs, meaning that it's going to be a 104.5 degree angle. And the reason is, for pretty much all of these, is that lone pairs repel more strongly than bonding pairs. There you go. It's literally always that. So that's not done though, because I haven't explained why this angle is this. They repel more strongly than bonding pairs, so the angle decreases from 109.5 degrees. The reason being is because if it was 4 bonding pairs, 0 lone pairs, then it would be tetrahedral 109.5. But because we're adding these extra lone pairs in, or I say adding, they're just now here, it starts to make this angle like narrower and narrower and narrower. There you go. So the initial rate of reaction between sodium thiosulfate and hydrochloric acid could be monitored by measuring the time taken for a fixed amount of sulfur to be produced. Describe an experiment to investigate the effective temperature on the initial rate of this reaction. Include a brief outline of your method, how you'll measure the time taken for a fixed amount of sulfur to be formed, how you will present your results in a graphical form, and then sketch a graph of what you would expect. It's always helpful to write down what your dependent and your independent variables are, because then it helps you shape your experiment and know what you're measuring and also like what you need to control. So our independent is what you're changing, and it's going to be changing your temperature. That's fine, right? But then we need to figure out how we're going to measure this. It's obviously tempting to just be like, oh, the rate of reaction. But you're not directly measuring it that easily. Instead, what you should say is what you're going to physically do yourself in the lab, in my opinion. So here, we're waiting for a fixed amount of sulfur to be produced, a fixed amount of solid and sulfur, which means we could use a technique that measures how much it takes to appear. For example, you could have a conical flask on top of a white tile and you can wait for the X to disappear, or you could measure samples using a colorimeter. So I'm going to use the white tile and see how long it takes to disappear. So the dependent is how long X takes to disappear. Now that you have that, you want to make sure that the only thing that's changing this is the temperature. So every other thing needs to be controlled and kept consistent. So then your method would just be this now. So method would be place conical flask with either the sodium thiosulfate or the acid, either's fine, with the acid on top of a white tile with a dark cross on it. Then what we do is we add the thiosulfate, or the other way around if you've done it, and start a stopwatch, and then time how long it takes for the cross to disappear. Then what you do is you would repeat at multiple temperatures using a water bath or something. And then giving examples, AG 10, 20, 30, 40, 50, etc., right? As well as that, we need to talk about making sure that we are doing, a valid experiment. So we need to keep the volume and concentrations of solutions constant as well. So that's a quick thing about method, right? And how we'll measure the time taken. That's that and that. How will you present your results in a graphical form, and then a sketch of the graph that you'd expect. So now that we've got that, let's talk about how we'd actually use our results. So use of results. So now at this point, you'll have a table, right? I'm hoping for anyway, that would have temperature here and time taken in seconds. This isn't a rate though, that's just the time it takes. A rate is going to be the change in something over time, but we don't have that something. We can't really measure the amount of the thingy, the cross disappearing. So whenever you have a time like this, you do 1 over t to get a rate like that in a general sense. So what we do is we calculate 1 over t for all results, or for all temperatures, for a rate. And then what we do is we'll plot 1 over t on the y-axis against temperature on the x-axis. And then you would draw a smooth line of best fit. Now, if we were to draw like a sketch of this, 1 over t and temperature. Now, if it was just t and temperature, right, it'd probably look something like that, like this, right? If we're doing 1 over t, what happens is it becomes a curve that gets bigger and bigger and bigger and bigger, bigger like that, right? Imagine at this point, that was 5 seconds, that's 50, but 1 over 5 and 1 over 50, right? 1 over 50 is teeny, 1 over 5 is bigger. So what ends up happening is the curve starts to look like this, where it shoots up like that, rather than it just being a singular line. So that's what it would end up being. There you go. Okay, so now it says draw the displayed formula of a molecule of H2SO4. So sulfur likes to be in group 6. 1, 2, 3, 4, 5, 6. Oh, because it's got a double bond there. All of them are used up. O here, and H2, H. There you go. In aqueous solution, sulfuric acid acts as a strong acid. The H2SO4 dissociates to form HSO4- and H plus ions. The HSO4- ions act as weak acids and dissociate to form SO4- and H plus ions. Give an equation to show each stage in the dissociation of sulfuric acid and include appropriate arrows in your equations. Anything in the universe that loses an H plus is an acid. Anything in the universe that gains an H plus is a base. So here it's told you the H2SO4 acts as an acid and dissociates into these ions. So you can write that immediately there. However, there's a multi-step thing to this. It's a strong acid, so the dissociation is really far to the right. What you end up getting is H2SO4 becoming H plus and HSO4-. That's the first part. But then it tells you this HSO4- can act as a weak acid. So it's going to lose an H plus, but because it's weak, it becomes reversible because the dissociation is very far to the left. So what you end up getting is HSO4- becomes H plus and SO4-. There you go. So a student is required to make a 250 centimeter cubed of an aqueous solution that contains an accurately measured mass of sodium hydrogen sulfate. Describe the method that the student should use to make the solution. So what we do usually is we measure a solid thing, we put it in this, we put it in a volumetric flask, we fill it up, and that will be the solution that we want. We do some calculations using, moles equals concentration times volume, and eventually find out what mass we'd need, but that's not necessary here in this example, so we're fine. So what we do is we need to describe actually weighing it here. They don't want us to do any numbers, they just want us to do, the actual procedure. So what you do is you will put a weighing bottle on an electronic balance and zero this. Because if you zero it, then you can weigh out this thing more accurately, because you don't really, it does allow it, but if you put, what I'm trying to get at is if you put the stuff in here and then you dissolve it and then transfer the washings into it, you won't lose any substance, you won't lose any solid because you're transferring the washings as well. So you can do that here. So then you add the required mass of NaHSO4, and then you would dissolve in a small amount of solvent within the weighing bottle. Then what you would do is you transfer this to a 250 centimeter cubed, because that's how much they want, volumetric flask, right? But we don't know if we've got still some left in that weighing bottle. We don't want to lose it. So what we would also do is we would wash out the weighing bottle with the solvent and transfer the washings as well. That way we don't lose anything to the volumetric flask. Then what you would do is you would fill the volumetric flask with your solution up to the 250 centimeter cubed mark, and then invert multiple times to ensure thorough mixing. This also means that it's all evenly distributed as well, but you have to say all of those steps. That's the only way to do it. So now it says a solution that contains this much NaHSO4 and 100 centimeters cubed as a pH of that. Calculate the value of Ka for this hydrogen sulfate ion that is behaving as a weak acid and give your answer to 3 significant figures. So we need to use the context of the question. It told you that the HSO4- ion can also act as an acid. So here, the acid, our HA, really is the HSO4- ion, right? So if we're using Ka, we have two options. We either have Ka equals H plus A minus over HA, or Ka equals H plus squared over HA. Now, to clear up some confusion on this topic, A minus, well, so HAs are acid, right, in these formulae. A minus is the salt, not the base, because OH minus would be a base. The reason it would be the salt here is because weak acids very barely dissociate. So for example, if I have like HA, H plus and A minus, because they're so far on this side, these numbers are practically the same, because it'd be like 0.0000001 and 0.0000002. You could treat them as if they're the same and it won't have a huge impact. That's why. But the moment you add a salt, it will dissociate into A minus and the other, like, sodium or whatever, right? And that makes that number come up. So you actually have to factor it in now. You can't just make them like equal. Here in this question, we have NaHSO4, which will dissociate into Na plus, and then this. And then this can act as a weak acid. So there's no salt in this here, right? So that means it's going to be this formula we're using. So here, we've got a bunch of steps to follow. We've been told the original NaHSO4. We've left it to dissociate and eventually form an equilibrium, right? That's what Ka is. It's an equilibrium constant, just like Kc, Kp, anything, right? We need to figure out how much H plus and, well, we can't really do with A minus, but how much H plus and HA we have at equilibrium. So here, what you can do is just quickly sketch out what this equation would be, which would be HA eventually becomes H plus and A minus. Now these are equal, remember? And then what you would do is you'd work out your initial moles, your equilibrium moles, right? So our initial moles of this whole thing would be, well, we'll have to come up a couple steps. We've been told this mass of NaHSO4, so we could work out the moles of NaHSO4, which would equal the moles of the HSO4 minus, because that dissociates into, this dissociates into that. So you'd end up getting 0.605 divided by, over its MR, which is 120.1, which ends up giving you 5.04 times 10 to the minus 3 moles, right? So then, initially, we have 5.04 times 10 to the minus 3 moles. This is pre-dissociation. This is before it's done anything, so that's going to be 0 and that's going to be 0. Now, once it's hit the equilibrium where it's, acting as its weak acid and stuff, we need to figure out how many moles of H plus there is. They've told you the pH here. So then H plus would equal 10 to the minus 1.7, right? 2, sorry. That's going to be, it's the same volume, so the moles of this would be 10 to the minus 1.72 times the volume, right? And then we need to figure out how many moles of this we have in the end. So the volume they told you was, 100 centimeters cubed? So it'd be times 100 over 1,000, right? If this has gone up by this much, this will have fallen by that much. So that means this is going to be 5.04 times 10 to the minus 3, right? Minus 10 to the minus 1.72 times that volume, 100 over 1,000. Which means on equilibrium moles are now going to be, so that's going to be 3.134 5 times 10 to the minus 3 moles, right, of this HA. Now, we need the concentrations to use this, so our equilibrium concentrations would just be this, so that answer divided by 100 over 1,000, which would be 0.031345. And here, well, that's just going to be the same as this here, isn't it? Like that's the concentrations. It's just going to be 10 to the minus 1.72. So then Ka would equal H plus squared, the concentration, so 10 to the minus 1.72, all squared, divided by the concentration of HA, which is going to be 0.031345. If we do that, we get roughly 1.15 times 10 to the minus 2. There you go. 1.15 times 10 to the minus 2. And the units would be, well, it's H per squared, mole per decimeter cubed squared over mole per decimeter cubed. You get mole per decimeter cubed. So this is an application of an equilibrium question, a common mistake, even one that I made when I was practicing back in the day with similar styles of questions like this, is by just using the same HA here. The thing is, though, that this will dissociate slightly into these two. So you have to work out what this is after it's dissociated, not just at the start. Otherwise, you would end up using more HA than there actually is, and you'd get a different value for Ka. If you're going to make H+, it has to have come from here. So if H+ is there to begin with after dissolving this, then that has to have gone down. So it's kind of an equilibrium question like that again. So some sodium sulfate is dissolved in a sample of this solution from here. Explain why this increases the pH of the solution. So if you have a look, in this equilibrium, we have HSO4 minus, and that dissociates into SO4 2 minus and H+, right? So they've told you that we've added sodium sulfate. That's going to be Na2SO4. The SO4 bit's the bit that we care about. What that will do is that'll increase the SO4 2 minus concentration, right? So what the equilibrium will do is, because Le Chatelier's principle says the equilibrium will counteract the change, the equilibrium will shift to decrease the SO4 2 minus concentration, and it will do this by reacting SO4 2 minus and H plus shifting to the left. What that does is if it's shifting to the left, H plus now drops. That decreases H plus, and therefore the pH would increase. There you go. Whenever you have an equilibrium question, I always say it's good to point out the change and then say the equilibrium will shift to, not just say counteract the change, say what the counteracting is. Either shifts this way, the equilibrium will shift to either decrease the temperature, increase the temperature, whatever, and then actually say which way left or right it goes. Because at least by just saying this first half, you could probably get a good mark or two from that, Rather than trying to think, oh, well, let's see which way it shifts first after juggling like 20,000 things. Like, I think it's obvious to just point out the change, point out what it would do to counteract the change, like the counteracting itself, what it is, and then how, by actually doing left or right, by reacting with X and Y. That way you can always like secure the bag, and it just means it's easier to spell out. I'm just going to point out what this mark scheme says here. So it's saying, name the piece of apparatus labeled A. That's just a salt bridge. Like, it's connecting the two there, right? These two half cells. However, if we have a look at the mark scheme, it says allow description, whatever, and then it says YouTube, not YouTube. We are finished, bro. We are actually finished. Y'all Zoomers, I'm Gen Z anyway, but like, y'all Gen Alpha kids, bro, need to get off the YouTube. You need to start watching the Mr. Beast videos and the Skibbity Toilet Man, because now it's coming up in A-levels, bro. We're finished. We're done. It's over. We're done. The last normal people were born after maybe 2000. Well, I was born in 2000, and I'm definitely like normal. Let's say 2002 at the absolute most. Anyone beyond that, bro, y'all are tweaking. Anyway, state the purpose of A. It's to complete the circuit. That's all. Because, one second, complete the circuit. The idea is that when you're moving electrons here, and there's a flow of charge this way, but you can't have a circuit without it being complete. Like, it won't work. So we need something else to carry charge across. This doesn't mean things are moving across, by the way. It just means that the ions in the salt bridge are either moving side to side. What that does is it allows a continued flow of charge across the entire circuit. Otherwise, it wouldn't work, right? It balances electrical neutrality, it balances charges. Because as electrons are moving from here to here, within the salt bridge, there'll be like K plus, for example, and NO3. They'll move side to side, and that keeps everything nice and balanced, and it works. Otherwise, it won't. So now it says you name the substance labeled B as the electrode. So we have a look. What we are doing is we're looking at the Fe2 plus Fe3 plus electrode, and that's your standard hydrogen electrode. Because we're changing from two things that aren't solid, like these are going to be aqueous and the one's going to be a gas and aqueous, we can't have an electrode physically from them. So instead what we use platinum, which is a surface for them to do the reactions on because it's inert. So it's platinum. Whenever you're switching between two things that aren't solid, one of them can't act as an electrode, so you have to do that. So now it says complete table 1 to identify C, D, and E from figure 1 and then include the essential conditions to each. So if we have a look, C here is the solution that the H2 is being bubbled into. So it has to be something with H plus in it. So any monoprotic acid. So HCl, and what's the conditions? 1 mole DM minus 3. You could do H2SO4 and make it half mole DM minus 3, but like you just want 1 mole of H pluses, that's why. Now what's going into this hydrogen electrode? Hydrogen gas, right? Because it's a gas, what we need to do is need to make sure it's 100 kilopascals because that's standard. That's what we use as our, baseline for everything. Here on this side then, what's E? It has to be a solution of FeCl2 and FeCl3 or Fe2 plus and Fe3 plus, and the conditions again, 1 mole DM minus 3. Otherwise you'll get differing values. And also, as well as that, we should really put the temperature 298 Kelvin. That can go anywhere here. Now it says the standard electrode potential for the Fe3 plus Fe2 plus electrode is plus 0.77. Give the ionic equation for the overall reaction in this cell. And then it says state the change that needs to be made to this apparatus to allow this reaction to go on to completion. So here, this is positive. And remember that your standard hydrogen electrode is always considered to be 0. So if this is more positive than the other one, that means that this is going to be reduced and the other hydrogen electrode is going to be oxidized. So what you end up happening is that you have H2 becomes 2H plus and 2E minus, and then your Fe3 plus will become Fe2 plus, plus E minus will become Fe2 plus. So then we need to times this by 2, and then we can combine the two of them together. So what you end up having, is you'll have H2 plus 2Fe3 plus goes to 2H plus 2Fe2 plus. Now it says state the change that needs to be made to this apparatus to allow this cell reaction to go to completion. So here, the reason we use a voltmeter, it's a bit of physics here really, but we want to make sure that the resistance in this is so unreasonably high so that no current can get through here. That way, it can measure the difference between the potential between these two, as in like the charges on each side, essentially. It's simple terms. So electrons will start moving whichever side to whichever side, right? But it can't get past here, and that's why we measure it with a voltmeter. It'll show you the maximum possible difference in potential, as in like the energy per unit charge. So all we can do is we could just replace this or remove it entirely and just let it do its thing so the electrons can freely move, and then it will do its entire reaction. So here you could just say remove the voltmeter, Or you could replace it with like a wire, ammeter, a lamp, anything that doesn't have like nearly, infinite resistance, really. So student sets up this cell, and then it says the results are here, and then it says complete the table. So all you do is you divide Zn2 plus its concentration by Cu2 plus it, divide these two, and then you ln the result. If you do that, you get 2.30. There you go. Now it says plot a graph of this against this, so E cell and then ln to, this ln value here. You should use at least half of the grid, and I'm just going to copy and paste this one sec. Wow, did you look at that? I did it perfectly. Whoa. And yeah, that it should be like at least half the grid. You should draw like a line of best fit, but it should be like a, a straight line, because they all look like they should be a straight line, if that makes sense. The equation shows how E cell varies with concentration. The equation is in the form of this equation for a straight line, y equals mx plus c. Calculate the gradient, and you must show you're working. Use a gradient to calculate T at which the temperature of the measurements of E cell were taken. If you're unable to get this gradient, then you should use a value of that. This is not the correct value. So what we need to do is compare the y equals mx plus c equation to what we have. So y equals mx plus c. Every single straight line graph in the universe will follow that. So we look at what our y-axis is now. So y-axis has now become E cell. So y would now equal E cell. And our x-axis is the ln stuff here. So now our x equals the ln, blah, 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 basically, right? So then what you do is rewrite this in this form now. So E cell equals m times ln blah, 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 right? Plus c, okay? If we have a look, this is our m that's times down to the ln thing here. Can you see how that is all times down to there? So that is your m. M is the gradient, remember. So m equals minus 4.3 times 10 to the minus 5 times t, which is the gradient. So to work out the gradient, all you do is you would do y2 minus y1 over x2 minus x1, right? So you'd pick 2 points and you'd work them out like that. So if I choose here and here, you'd do, this would be your x2 and your y2, and this would be your x1 and your y1. Now for the mathematicians that lose their mind every time I say this, it's because not everyone does maths, and some people get the numbers mixed up and they'll get the gradient wrong. So I always just say, stick to using this as your second most coordinate and that to be your first most, and as you move more and more to the right, that'll be like, a higher number, rather than doing it the other way around and mixing the numbers together. Because you should end up with a number that's negative because it's a downwards graph, right? So then here, if you work out the gradient, I'm just going to skip ahead and say I've done it. Whoa, look at that, I'm so amazing. It should be roughly 0.013, right? So that means that this gradient here, minus 4.3 times 10 to the minus 5t equals 0.013, well, minus that, sorry. And let me just write that there. So then your temperature would just equal minus 0.013 divided by minus 4.3 times 10 to the minus 5. If you do that, you end up getting 302 Kelvin. There you go. So now it says in experiment 2 in table 2, the electrode potential of this is the Cu2 plus Cu electrode is that. Use data from table 2 in question 3.6 to calculate the electrode potential for the Zn2 plus Zn electrode in experiment 2. Give one reason why your calculated value is different from the standard electrode potential for the Zn2 plus Zn electrode. Fine. So here they've told you this is experiment 2, and they want you to find the standard electrode potential for the Zn2 plus electrode. So we have a look here. That's going to be our minus 2.3, the ln of this whole thing. And the E cell, they've told you, is 1.13. Fine. Now, let me just scribble that down. The E cell is going to be 1.13. And so we need to, they've told us, so the E cell of that was from the table, 1.13. And they've told you that the E for the, the E value for the Cu2 plus electrode, blah, 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 is 0.33 volts. So the formula is E cell equals E reduced minus E oxidized, right? We need to figure out if we can try and find out what the other one is, or we're kind of screwed, right? So here we have one of these possible things, either reduced or oxidized. We need to figure out which one it is. So we have a look back here. This is our conventional representation. So if we have a conventional representation, what goes on the left is the one that's oxidized, what goes on the right is the one that is reduced, right? So that means that this one's on the right, so that one's going to be reduced. So our E cell, so our 1.13 is going to be reduced, so 0.33 minus some mysterious number, E ox. So then E ox would equal, so you move that across there, it would equal 0.33 minus 1.13, which if you do that, we get minus 0.8. There you go. So there you go, minus 0.8. But use the whole question. Then it says, state why your value is different from the calculated standard electrode potential for this electrode. Well, I mean, if we have a look here, this is a student setting up with this. They're not doing the standard electrode potential, so it's probably not going to be in standard conditions. The temperature might not be consistent. It's all just, they're just doing it in a lab. So immediately, that's why. Because the standard electrode potential is running in perfect conditions. So in this case, it must be that there's just non-standard conditions. That's the only explanation. So it could be that the concentration of Zn2 plus is not 1 mole per deciliter cubed, or it could be the temperature is not right, and so forth. But, that's enough, to be honest. So ethanol reacts with potassium cyanide followed by dilute acid to form 2-hydroxypropanenitrile. So remember that ethanol is a carbonyl group, so you've got a C double bond O, and it's reacting with Cn minus, really. And then for some reason you end up with this Cn has been stuck on here, and then an OH like that as well. So the mechanism by which that's happened is that, well, you can see this is joined onto this carbon, right? So that's going to be addition. And the reason it joined onto this carbon is because that carbon's electron deficient. It's given a lone pair of electrons to this carbon to form a bond. So that means it's nucleophilic because it's an electron pair donor. There you go. So the 2-hydroxypropanenitrile formed by this reaction is a mixture of an equal amount of two isomers. State the name of this mixture, or type, and explain how the structure of ethanol leads to the formation of two isomers, and then draw 3D representations of the two isomers to show the relationship between them. So the reason that you've got these two mixtures is because you're going to be making chiral carbons from this. Because if we have a look, we have CCN with an H, an OH, and then whatever this is what. So that's going to be H3C from before, because we've made 2-hydroxypropanenitrile. So 1, 2, 3, propanenitrile, 2-hydroxy, right? Can you see there's a chiral carbon? We'll have optical isomers. When you have an equal amount of optical isomers, you have a race mixture. We need to explain why this happens, then why you get an equal amount. If we look at the original thing, we're looking at ethanol, right? Ethanol looks like this. Well, blah, 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 C, whatever, and then an H here. If we focus on this part here, there's 1, 2, and you can treat that as 1, so there's 3 bonding pairs, 0 lone pairs. So you actually have a trigonal planar bit around here. Because it's planar, that Cn minus can either attack the carbon on this side like this, underneath, or it could go over like that, if that makes sense. So again, it could be here, or it could be there. And as a result, you get equal amounts of the two of them. There's an equal probability of attack on either side. So that's exactly why you would explain it. And that's how you explain this, is that the C double bond O is planar. So there's an equal chance of attack by Cn minus on either side. And this ends up with a race mixture, or race mate. Mixture. So the 3D representations, we're showing the isomers that have been made. Start by drawing the chiral carbon in the middle and then just add the rest in. So there's an H on it, there's going to be a wedge coming out here, there's going to be a dotted line to a CN, and then you've got your OH here, and then the rest of it there, which is an H3C, because remember we're making 2-hydroxypropanenitrile. Then all you do is you just draw the mirror image of the thing there. So then it's going to be NC, H here, CH3, and then OH like that, or H here. There you go, that's it. So 2-hydroxypropanenitrile can be used in the synthesis of this monomer, acrylonitrile, suggests a suitable reagent and conditions for the conversion of 2-hydroxypropanenitrile into acrylonitrile. So we need to compare what we have. We have CH3, CH, OH, CN, right? And if we have a look, so let's wait, 1, 2, 3. Yeah, so that's what we have. So what's changed between here and here? Well, we had an alcohol, now we have an alkene. So we've booted off the alcohol bit and a hydrogen with it. We booted off water. So this is going to be concentrated strong acid like H2SO4, and it's going to be heated as well to remove that water. We're dehydrating it here. So now it says draw a section of the polymer of polyacrylonitrile showing 3 repeating units. If the question says repeating units, then you leave the ends open. If it doesn't, if it just says showing 3 units or something like that, or show the thing when 3 of these join together and it's not repeating, then you can close the ends. Now we need to figure out what type of polymer this is going to form. So it's an alkene, so it's going to form addition polymerization. If it was something like a carboxylic acid on one end and an alcohol on another, or like a diamine or a diol and anything like that, then you could get polyesters and polyamides. But here, this is just a double bond here, so it's going to open up. So what you do is you just open the double bond and you write the groups up and down here. So on this carbon here, there was an H and an H, and then on this carbon, there's an H and a CN. Right, that's one singular repeating unit. So there's the empty bit there. We want another, so 1, 2, same thing, H, H, CN, and they want another because they want 3. So C, C, open that up, H, 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 CN. And that's it. There's your addition polymers, 3 of them. The percentage biomass of iron in a steel wire is determined by a student. What they do is they get 680 milligrams of this wire in an excess of sulfuric acid, so all of it forms Fe2+. They make it up to exactly 100 centimeters cubed. They take 25 centimeter cube portions of this and titrate it with potassium manganate in solution. Fine. Then it says, given an equation for the reaction between iron and sulfuric acid. So start by writing what you know, right? So we have Fe. We're going to react H2SO4. What are we going to end up making? Well, a metal plus an acid will make a salt, FeSO4, plus hydrogen gas, H2. That's it. Now it says the titration results are shown in this. Calculate the mean titer. So when we work out the mean titer, we want to use concordant results. Concordant results are the ones that are within 0.1 of each other. This one is not within 0.1 of this or this, but these two are. So the mean tide is 22.7 plus 22.6 over 2, which gives you 22.65 centimeters cubed. There you go. So then it says, give the overall ionic equation for the oxidation of Fe2 plus by manganate ions in acidic conditions. All you do is you write down what you know first, okay? So we know that we're going from Fe2 plus and we're reacting manganate ions, which is MnO4 minus, right? Now it's told you that this is being oxidized. The only other oxidation state you guys know for iron is going to be Fe3 plus. If that's been oxidized, this must have been reduced. And the other form that this gets reduced to is Mn2 plus. All right. Now, a lot of people like to balance all the stuff out, add the waters, and then finally the electrons in the end. I think you do the electrons first. So number one, do the electrons first, and then everything else falls into place. From here to here, that has lost 1 electron, right? This has gone from 8, so that's minus 8. That's going to be plus 7 oxidation state to plus 2. So this means it's gained 5 electrons. So again, this has lost 1, this has gained 5. So in order to balance that, we need 5 of these to provide 5 electrons to the Mn to become that. So we'll have 5 Fe2 plus and then 5 Fe3 plus. So the rules are you balance the electrons, then you balance all of the elements except hydrogen and oxygen, unless they are being oxidized or reduced as well. Then you balance the oxygens by adding waters in, and then finally the protons, in my opinion. So here we've balanced the Fe's on this side, there's enough Mn's to go, but we have 4 O's here, so I'll add 4 H2O's on this side. But now we have too many H's and we have none here, so then we'll add 8H plus here to fix that, and then the problem solved. And you can check the charges overall, and it adds up. It says here the acidic conditions gives it away that there's an H plus here. If it were to say basic conditions, you never know H minus there. But there you go. Now it says state the color change seen at the end of this titration. So it's going from Fe2 plus, you eventually get that Mn2 plus, so it's going to go pale green, and it will end up becoming pink. So now it says name the apparatus used for each stage of the methods. If you want 25 centimeter cube proportions accurately, we're going to be using a pipette. And then adding the potassium manganate. So remember that this potassium manganate, where is it? That's being titrated into it, so it's going to be a burette. There you go. So now it says the balance used to weigh this iron has an uncertainty of plus or minus 0.005. This is weighed and its mass is subtracted from the total mass of the container and the wire. Calculate the percentage uncertainty using the balance. So your percentage uncertainty is going to be your uncertainty over the value that you got times 100, right? Now they've told you here that this balance has an uncertainty of plus or minus 0.005. We weighed it and its mass is subtracted from the total mass. So we've done 2 readings. So the uncertainty here is going to be 2 times 0.005. And the value we measured, grams, milligrams, I need to convert that to milligrams or grams. I'm going to change this to grams. So 0.68 times 100. If you do that, you get 1.471, which is roughly 1.47%. There you go. So now it says what amount of sodium hydroxide would react exactly with this much diprotic acid, and it's got an MR of that. So what we need to do is we need to quickly sketch an equation for this, right? So we've got a diprotic acid, and it's going to react with NaOH. Now, because it's diprotic, you're going to need too many as NaOHs as you will acid, right? That's cool. So now we can figure out the moles of each thing, and then we can try and work backwards because they've given you concentrations and volumes. So the moles of the acid is going to be, well, its mass, 7.5 over its MR, 150. If you do that, you get 0.05 moles. Therefore, the moles of the NaOH you would need would be 2 times this, so it'd be 0.1 moles. Now all you have to do is pick whichever answer gives you 0.1 moles. So what you do is you do 50 over 1,000 times 0.05, that first one is a no. Then you would do 100 times, divided by 1,000 times 0.5. If you do that is also a no. Then you would do 100 divided by 1,000 times 1, and that is indeed a yes. So the answer is C. There you go. So lead nitrate and potassium iodide react according to this equation. Fine. It says in an experiment, 25 centimeters cubed of a 0.1 mole per deciliter cubed solution of each of these are mixed together. What amount of lead to iodide is made? So real quick, N equals CV, so just quickly work that out. It would be 25 over 1,000 times 0.1, which ends up giving you 2.5 times 10 to the minus 3 moles of both of these, right? So then it says how much lead iodide are you going to make? So you've now got the moles of this and this, right? Now here, can you see how that's in a 2 to 1 ratio? If we have 2.5 times 10 to the minus 3 moles of this, we have excess of that for this reaction because you only need half of that, right? So 2.5 times 10 to the minus 3 of this will react with the half of that, which would be 1.25 times 10 to the minus 3. Even though we have 2.5 times 10 to the minus 3 of this, we will run out of that no matter what. So there's no other possible way to get further than that reaction. So the absolute most you can make is going to be the same as this, which is going to be 1.25 times 10 to the minus 3, which is A. You could have an infinite amount of this until when that's run out, you will have used up 1.25 times 10 to the minus 3 of them, because every one of these reacts with 2 of them. Nitrogen dioxide is produced from ammonia and air as shown in these equations. What's the enthalpy change for this following reaction? So here we need to use Hess's law and we need to construct the weird cycle. And the only way to do any questions on enthalpy changes is by cycling it. So if we have a look here, we've got 4NH3, there's a 4NH3 here, 7O2, but we only have 5O2 here, right? We could take an alternate route. If I just number that as 1 and 2, we could take an alternate route where we end up doing reaction 1, right? And that will give us this. But we don't have NO here. We only have NO2s. So maybe, can you see how that NO here and that NO is there? So I could do this reaction first, number 1, and then do number 2 after it, right? But the issue is that that's 4NO, that's 2NO, and also we need, like there's 5O2s and there's only 1O2 here. So we actually need 2 lots of this reaction 2. And if we do that, we end up doing reaction 1, which makes this, and then we do reaction 2, which then makes this, which fits the bill, because that first reaction makes the water, and the second one will make those NO2s, like this. So Hess's law says that the enthalpy change of this, right, for as long as you start and finish at the same reactants and products, will be the same as the other route. And because we're starting and finishing, can you see we're starting with this, and we do make this in the middle, but then that goes away to make this. So we finish with this, right? And also there's the extra 2's there. The enthalpy change is the same. So then the enthalpy change of this reaction here would equal the root 1 minus 909 plus 2 lots of the root 2. So plus 2 lots of minus 115. If you do that, you end up getting minus 1139, which is D. That's how Hess's law cycles work. So which of these changes leads to a higher concentration of SO3 in the equilibrium mixture? What we want to do is we want to shift it to the right. We know it's exothermic, so let's see if any of the temperature ones we can knock out straight away. If it's exothermic, decrease in the temperature will make it go that way, so higher temperatures out. Next, these are gases. We can see that we have, 3 moles here and then 2 moles here. So if you have a higher pressure, that'll shift it to the right. We can see lower pressure, that's out. And immediately as well, catalysts will accelerate both the forward and reverse equations, so it does not change the equilibrium amount. So that's D gone. So it has to be A. And if you look at that as well, you can use concentrations as well in gaseous equilibria. If you increase O2, the equilibrium will shift to decrease it by moving to the right. So that's got to be A. So here, the results of an investigation of P and Q is shown in this table. The rate equation is rate equals P times Q squared. So here, if we have a look at P, what they've done is they've times it by 3, and what's happened to the rate is times by 2. So that means that what we've done here, surely that should, so that means if we do some change here, that would obviously do the change squared to this thing, because it's, second order. So that means x squared times by 3 equals, timesing by 2, right? So that means that x squared has to be 2/3, so x has to be the root of 2/3, which is timesing by 0.8165 to get here. So then what you would do is you would just do 0.5 times the answer, right? And if you do that, you end up getting 0.408, which means it's C. There you go. Now it says the equation for this reaction between sulfur dioxide and oxygen is shown in an experiment. 2 moles of sulfur dioxide are mixed with 2 moles of oxygen. The total amount of the 3 gases at equilibrium is this. What is the mole fraction of sulfur trioxide in this equilibrium mixture? So it's a multi-step bit here. What we need to do is we've got to figure out, so mole fraction, remember, is the moles of the gas over total moles. So we know that the total amount of these at equilibrium is going to be 3.4. So we know total equals 3.4, but we don't know how much sulfur dioxide decreased and how much of these ended up being made, right? So we need to quickly sketch out like one of those, little table thingies. So the 2SO2 then plus O2 becomes 2SO3, initial moles, final moles, right? So initially you will have they will have 2 of this and 2 of this, and then we'll have 0 of that. The final moles would be X of this because we end up making some. So this will have dropped by, so 2 of these makes 2 of them. So that will be 2 minus X. But then here, that will have gone down by 2 minus a half X because you can see there's a 2 to 1, right? So that means that this total moles equals, so 2 minus X plus 2 minus a half X plus X equals the total of 3.40, right? So then if I simplify this, so 2 plus 2, 4, minus X minus a half plus 1 equals minus a half X equals 3.40. So then minus a half X equals minus 0.6. So then X would equal 1.2, right? So cool, because now we know this. We know that X was its moles, remember? So X equals 1.2. So the mole fraction is now just going to be 1.2 divided by the total moles, which they told you was 3.40. If we do that, we get 0.353, which is B. There you go. Nitrogen reacts with hydrogen in this exothermic reaction, which change increases the equilibrium yield of ammonia but has no effect on the value of Kp. So immediately, anything that affects Kc, Kp, Ka, Kw, K anything is temperature. So I can immediately get rid of the temperature one because that will change Kp, right? Now what we want to do is we want to increase the yield of ammonia. So this is an exothermic, so decreasing the temperature would make it go this way, but remember, we don't want to change Kp, so that one's out. Here we have, 4 moles and 2 moles. So increasing the pressure will make it shift that way, so that pressure one's out, right? So the next things are, we are stuck without a catalyst. Well, that won't, because it will accelerate the forward and the reverse reaction by the same, so that one's out, so it's got to be B. And if we have a look at B as well, partial pressure is like the concentration of a gas. If you're increasing this much partial pressure, it's going to move to counteract the change. It's going to shift to try and decrease its partial pressure by going that way to make more of this. There you go. So the E values of the 2 electrodes are shown. What is the EMF of the cell? This and this, right? So it's going to be E cell equals E reduced minus E oxidized. They've told you which one it is. It might be tempting to be like, oh, this must be oxidized, so it's reduced, right? But we need to just double check that there's no other like funny stuff going on here, right? The one on the left is the more negative one that's going to be oxidized. The one on the right is the one that's reduced. So in this case, it's FeS and FeS, Fe2 plus aqueous and so forth, right? So it looks pretty all right. Here it would just be 0.34 minus 0.44, which is plus 0.78, which is A. The reason I say not to just jump straight into that is to just double check they're not running the cell in the opposite direction, or they're not purposefully telling you, it's this and this. I always just make sure to check. Here it's fine because that is oxidized and that is reduced, so we're fine. It says which atom has the greatest first ionization energy, so that's the energy required to pull an electron off an atom, right? So we need to find out, so remember that you've got your nucleus and you've got your electrons orbiting it like that, whizzing around. We need to make sure whatever we choose has the strongest attraction between these, as in this is pulling on that as hard as possible, right? So whatever this is going to be in the smallest period with the highest nuclear charge. So if you have a look at the periodic table, in hydrogen we have 1 proton and 1 electron. Here we have 2 protons and 2 electrons. They're in the same period, so there's no extra shells and no shielding. However, the nuclear charge of this is higher because we have an extra proton. So that means it has to be helium. Lithium and neon, all of those are in the next shell, so there's some shielding immediately. So by that, it has to be the helium. What's the correct observation when barium metal is added to an excess of water? So when you're adding like group 2 metals in general, except for magnesium, they will react to form a hydroxide. And as well as that, a metal plus water makes a hydroxide, so it's got to give out H2 as well to keep the equation balanced. So it's going to bubble and form a colorless solution, which is going to be B. It doesn't make a colorless solution only because the equation is barium plus water makes barium hydroxide plus hydrogen gas. It would not balance that equation out. It wouldn't be possible, so that's out. White precipitate only happens if you make barium sulfate, so that's out, or carbonate, and there's none of that here. And also the same for this as well, so it's got to be just B. An aqueous solution of a mysterious salt gives a white precipitate when you mix it with silver nitrate, and then when you mix it with dilute sulfuric acid. What is this mysterious salt? So some salt is mixed with aqueous silver nitrate, right, and it'll give a white precipitate, but it will also do it if you put it with sulfuric acid. So we know it has to have chloride in it here for this part, but when you mix it with sulfuric acid, you also get a white precipitate, which means it's going to have to be a barium sulfate formed here. So it's got to be a barium salt that has Cls in it as well, which is immediately A. Whenever you're mixing sulfuric acid and you're getting a white precipitate, you got to hedge your bets. It's probably going to be a barium sulfate they're finding here. Now, which statement is not correct about the trends and properties of the hydrogen halides from HCl to HI? So if we have a look, what's not correct? The only thing that's changing is from HCl to HI, you're going down the group. So the halogen that's on this is going to get bigger and bigger and bigger and bigger, right? So if it's getting bigger and bigger and bigger, then that means think about what's going on here. So HCl and HI, if you're boiling them, the only bonds that are between them are going to be the permanent dipole-dipole interactions and van der Waals forces. The van der Waals forces, there's no hydrogen bonds because there's no H bonded to F or NOF. If you go down the group, the number of electrons in Cl to I are getting more and more and more. So the van der Waals forces are getting stronger and stronger. So immediately the boiling point gets higher. So that's already incorrect because it wouldn't decrease, it gets higher. So what's observed when you're adding concentrated hydrochloric acid to aqueous solution of CuSO4? Now, if we're looking at that, what we're really having here is we've got Cu2 pluses and SO4 2 minuses, right? But if you go one step further, it's a transition metal. So you've got CuH2O6 2 pluses and SO4 2 minuses. And now we've just added loads and loads of H pluses and Cl minuses. Any idea what might be going on? Cough, cough. What happens is these H2Os could swap with those Cl minuses and you end up getting a different complex ion. So it will change color, but you still have a solution and no precipitate would form, which is immediately D. A colorless gas is evolved. Well, what would the gas be? There's no carbonate here, so that's out. And again, for the same thing, we won't have a gas because there's no carbonate, so that's out. And then a precipitate forms that dissolves in an excess of concentrated hydrochloric acid. What the precipitate, even if we were to have like CuCl2, that's not really going to form a precipitate, so that one's out. So it's only got to be D. So now it says, what's the most suitable reagent for detecting the presence of carbonate ions in the presence of an excess of sulfate ions? So what we want to do is we want to eliminate carbonate ions, and they've already got loads of sulfate ions. So the thing we're going to do here is we're going to have to add a strong acid, and it will obliterate those, right? So if you look at NaOH, that's basic, and this carbonate ion can act as a base as well, so it's not really going to do anything, that's out. H2SO4, it will react to the carbonate ions, and it won't muck about with these sulfate ions, and it will make them get rid of those. So that's pretty good. It will make them, bubble and disappear. That's good. BaCl2, what it will do is end up reacting with the sulfate, and you'll get barium sulfate, but then you'll have mixtures of carbonates as well, so that's out. NaCl wouldn't really do anything in this reaction either, so it's got to be just B. So methylbenzene reacts with a mixture of concentrated nitric acid and concentrated sulfuric acid. What is the mechanism for this reaction? So here we've got this benzene chilling with this methyl group on it. What it ends up doing is you'll end up making an NO2 electrophile, which will join onto this wherever, right? And then it'll form a new bond here, NO2. But the problem is that there's too many bonds around this carbon, so H breaks and this, remember, that ring opens up. In summary, what we're really doing is we're swapping one of the H's on the benzene for an NO2. So it's substitution, so immediately you're out and you're out. Now, whether it's nucleophilic or electrophilic, the reason it's... So if we have NO2 plus, remember, that's going to go for the benzene ring, which is nice and electron rich. So it's attracted to electrons, so it's electrophilic. It's electrophile, B. There you go. Anyways, I hope that helped. Please like, share, and subscribe, and you know the drill. Thank you.